Hello everyone, I am Abdurrahman and today I will be presenting our paper Illuminating Darkness, Learning to Enhance Low-Light Images in the Wild. Here is today's roadmap. I'll start with the introduction and current challenges in low-light imaging. Then I'll present our core contributions, the LST dataset and the TF-former architecture. Next, we will review the experimental results against state-of-the-art methods and finish with our concluding remarks. Before introducing our solution, we identified two critical bottlenecks, data and architecture. First, the data. Existing datasets rely on synthetic dimming using low ISO settings. As the histogram on the right show, they completely miss the complex sensor noise and dynamic range of real high ISO photography. Second, the methods. Currently, architectures struggle. RGB methods tend to mix noise with details, while Retinix methods often create halo artifacts. Our objective is to solve both by collecting a large-scale real-world dataset and designing a model that effectively handles these specific challenges. Our work makes three major contributions. The dataset LST, we collected over 6,400 high-res pairs across 15 different camera sensors. As the chart shows, this scale and diversity far exceed previous datasets like LOL or NCLLI. The model TF former, we propose a tuning fork architecture that decouples luminance and chrominance. By processing structure and color separately, we eliminate the artifacts common in RGB methods. The results are clear. We achieve a 2.45 decibel gain over state-of-the-art methods and crucially boosted downstream object detection by 6.8 MAP, where standard models failed. Our collection pipeline ensures high-quality alignment in three steps. Multi-frame acquisition. We use three-frame capture strategy, reference low reference to guarantee temporal alignment between the noisy and clean images. Expert verification. Here, human manually inspect these pairs discarding over 1500 scenes that had motion blur or focal shift. Patch refinement. Finally, we use a classifier to automatically filter out low-quality patches, such as those with overexposure. This gives us a diverse mix of DLI ISP processed and NLI raw noisy inputs covering both input and indoor and outdoor scenes. You can see the high quality of these aligned pairs in samples at sea. Models often mix noise and detail. TF Former solved this with a tuning fork design. First, we decouple the image into light, luminance, and color chrominance streams. By encoding them separately, we can denoise the structure without washing out the colors. Then we use cross-attention to fuse them back together, ensuring the final output has sharp edges and accurate colors. If you look at the images on the top left, you can see that our method produces the cleanest and most natural results. This visual clarity improves downstream tasks as well. The radar chart on the top right shows a massive boost in object detection for challenging classes like chair and bottle in X-Dark dataset. Furthermore, the bar chart below shows that in a blind study, 15 human raters overwhelmingly preferred our results over models trained on older datasets. TF Farmer sets a new standard. We consistently outperform top models like Retinix Farmer by over 2 decibel across all lighting conditions. As shown in visual comparison below, this results in significantly cleaner images with accurate colors where other models fail to remove noise. Our evaluation studies confirm that both our data strategy and model design are optimal. On top, you see that filtering training patches yields the best results. On the bottom, the stepwise breakdown proves that every component of TFormer, especially the fusion and refinement blocks, is necessary to achieve state-of-the-art performance. Our model works on any camera. From DSLRs to compressed video, the visual results are consistently clean. User studies back this up, showing over 80% preference for our method across all tested scenarios. To recap, we contributed in three key areas. We built LSD, a massive dataset that solves low-light data scarcity. We designed TF-former, which decouples light and color for superior restoration. We proved that this approach generalizes across devices and boosts object detection. Moving forward, we plan to address extreme low-light scenarios by unifying enhancement and detection into a single pipeline. Thank you for listening. If you have further questions, please refer to our paper.